Okay, so what I'm going to talk about is more about the architectures of different types of firing systems, because there's quite a lot of different systems around that all work in slightly different ways, and depending on your need and what type of jobs you're doing, it makes a difference how these systems work. And also, if you're trying to diagnose issues with the systems, knowing a bit more about how they work under the hood as such can be quite useful. So we're going to get a little bit geeky, but it's a bit technical, but hopefully we'll be all right, and we'll see how we get on. So again, a bit about me, which you know already. The last thing that I have NDAs, which are non-disclosure agreements with some of the firing system manufacturers, and some of them say I'm not even allowed to tell you who I've spoken to, and others say I'm not allowed to divulge the information about how their systems work. So I speak quite generally in general terms about things, and my own systems, the ones I've built at uni, I can tell you exactly how they worked and all the ins and outs, but others I have to speak more generally about. So the architecture of a firing system actually affects the health and safety aspects of using the system. I think understanding the architecture helps you when you're choosing a system, diagnosing issues, and choosing the correct system for a job, a particular job. And also, if you're building your own firing system, understanding how some of these things fit together can be quite useful. So this is a little bit geeky, so I'll click through a lot of these. So in computer science terms, there is what we call an OSI model for protocols, for communication protocols. So the very bottom here is the physicals. This is your wires. So in your house, if you've got sort of broadband, or you've got a network in your office, this is the very low level. So it defines all the electrical characteristics, the cables, connectors. And then as you go up the stack, different layers of the model provide different features. So if it's got, if it's an Ethernet, a network like the internet, different layers provide different things like routing and communication and encryption, error correction and things like that. Right up to the top level, which is your application. So whether that's, for example, Internet Explorer, something like that sits right at the top. So the reason I'm telling you about this is because different systems have different levels of protocol and have different amounts of protocol in them. So the first protocol I'm going to talk about is RS-485. So RS-485 is a very standard industrial protocol that has been used for a very long time. It's used in all sorts of industrial communications, and it's used in a lot of firing systems as well. And it's a very, RS-485 defines the electrical characteristics, so the type of cable, the voltages on the cable. It doesn't define the data you're sending down it. All it defines, like I say, the very bottom layer there. It's a multi-drop protocol, which means you can have multiple boxes all connected and they're all daisy-chained together. The specified maximum distance is about 1,200 meters. You can get more than that. Sometimes it's less, depending on what's going on around it. I won't worry about the other things. If you know anything about computers and computer science and protocols and stuff, it's a differential protocol, but it's polarity sensitive, which means you have to get the wires the right way around for it to actually function. Like I say, it's used in a lot of industrial stuff. If you've ever done any intelligent lighting, sort of disco or theatre and stuff, this is not DMX. DMX is a higher level protocol. So if you ever watched if you've ever been to a concert and all the fancy lights, that's controlled by a protocol called DMX, which runs on RS-485. But the firing system technologies do not use DMX because it's got no error correction, no error detection and that kind of thing. So people often think that RS-485 is DMX and vice versa, but they're different levels in that protocol stack that we were talking about. So again, like I say, it's a bus network, so you've got your controller at the beginning and you've got this multi-drop type scenario. And there's various things, if you look at the specifications, about reducing noise by sticking a resistor at the end of it. But again, we're getting a bit technical, a bit geeky there. So, like I say, the protocol, very low level, it's at the physical, so it just defines the electrical characteristics. And then as you move up, you see that the firing system software is what's actually doing all the work. So the firing system software will deal with all the packet creation of data and all the error checking in the protocol. And then at the very top level, you've got your firing system software. So it's very simple, it's very predictable, the timings are very predictable because literally the data goes on the network, all the modules receive the data, they can decode it, and the time through this stack is very, very predictable, which is why it's used in a lot of systems. So like I say, a lot of systems use RS485. Some systems have strayed from the specification a little bit to make it easier to use. So they put power over it, made the data lines polarity insensitive and stuff like that. 9600 baud, which basically means 1 byte of data takes 1 millisecond to send down the network, is used by a lot of systems. Certainly the Merlin one we got here uses that. It's very, the RS485 sort of protocol is very simple to implement, it's simple to set up, which is why it's used a lot. And like I say, it's very predictable in terms of how long the data takes to get down the network to the firing systems, which you'll see why I'm explaining this in a bit. So issues with RS485, if you break the cable, if you drop a shell on it, you blow the cable, you can lose communication to your modules. It's a master-slave configuration, so that the controller is what's doing all the work. It's either sending the commands or requesting things from the modules. I put this down. This is an issue and also a benefit, but the issue is that the manufacturer is in total control of the protocol. So if they want to do anything clever, they have to write all that code themselves. They're not just taking a library and using it. They're actually having to develop this themselves. So the next type of system I'll go on is a radio mesh. So there are new systems that have come out in the last few years built around radio mesh systems. And what a mesh is, so say you've got this controller here, and the red line shows you how far this box can transmit. So we've got a firing module there, and that's obviously in the field, it can receive the signal. And that's how far that module can transmit. So we've got another firing module there, it's just on the edge, but it can receive it, and that's how far that can transmit, so on and so on. So in a traditional system where you have a radio broadcast, it broadcasts to the modules, they receive it. Only these two modules here would receive the signal. And the other modules wouldn't, because they're all out of range of the main controller. But the point of a radio mesh is that the messages can get bounced through the different modules, so that it eliminates the need for the main controller to be able to communicate to anything. So what it creates, radio meshes are very useful for high reliability networks. They're used in industrial situations where it doesn't matter how the data gets to the modules, but as long as it gets some way. And these modules are all in charge of their own routing and understanding where to send this data through this network. So for example, if we lost a module there, the data can route round it. And again, you can see in that scenario, you can lose various modules and the data will still get through to the last modules. So mesh networks, they're very robust. They're quite low power consumption because you're not beaming out a ton of power from one controller. They can be more low power because they can relay their messages across. There's a lot of pre-built modules that people use for radio mesh systems because there's a lot of protocol in there to do all the fancy routing and mesh side. So there's lots of pre-built modules that people use, and you can just slap them in if you're designing a system, and you can use that to deal with all that part of it. So looking at our OSI model layer again, you can see that the bottom parts of it here are all defined by the Zigbee Alliance. So I'm talking about a Zigbee mesh here, which is a particular type of mesh network. Those parts of the protocol are all defined. So all the routing, security addressing, all the discovering of where the modules are, that is all defined by them, and that's what these modules you buy actually give you. And then right at the very top is your firing system software. So, although they're very reliable, it does abstract a lot of the complexities away from the designer of the system. All you need to do is say, right, I need to send a message, send it, and it will go out on the network. But equally, because this data's got to get up through this stack and it's got to do a lot more work, you can have issues with how long the data takes to process because it's doing a lot more clever stuff. It will receive a message, decode it, and it will say, right, well, this is not for me, it's for somebody else. Well, I know this I need to hop through these modules to get to that, and then it will resend the packet out. So, like I say, the high level of protocol can create latency issues where if you've got a packet that has to be relayed through multiple devices, it can add a delay to the packet delivery. And how big that delay is depends on the type of mesh and the technology that it's using. But obviously, as technology moves on, these things get better and better and faster and faster. So when I was doing some research for this, I was looking, and some people have measured a hop between a node up to 20 milliseconds, which means if you can, normally in a site like this, everything will be able to communicate with everything else, so that the chances of having an issue is very low. But if you have a very big site where you may have to hop through multiple modules to pass these firing messages across, that could potentially be an issue if you have lots of modules. But again, this is just an example. There are many different mesh systems, and the level of the latency can depend on how they're designed in the protocol and everything inside them. You do have limited control on the route planning and how it deals with that, because that's all defined in the standard for the mesh. So like I was saying earlier, RS485, like serial protocols, give you very consistent delivery times of messages, whereas meshes can, and not just a mesh, any system with a high level protocol. For example, the system that I built when I was at uni used a industrial building automation technology, and again that had a huge amount of protocol in the stack, which meant it was very easy for me just to send a message on the network and then have the modules receive it and process it. But it did it took all the complexities away, which is nice, but equally it means you lose control. It doesn't mean these types of systems or these type of protocols are bad or not the right thing to use. It just means when you're designing it, it's just something that people need to consider when they're designing these systems. Yeah, like I say there. So the next part of this, so we've talked a little bit about protocols. The next part, I'm going to talk about autonomous and non-autonomous systems. So autonomous systems, like the Merlin system we've got here, is where the sequences are uploaded into the modules. So each of the modules knows their part of the show and what they need to fire when. So yeah, the firing modules can run their own sequences. The firing controller only sends sort of start signals and synchronisation signals to the modules, but fundamentally the modules are autonomous and they work on their own. So my feeling is autonomous systems are highly reliable because they're sitting there, they're doing their own thing. There's no problem with laptops or cables being broke. The firing module can carry on and do its own thing. So yeah, firing, and also because you're not reliant on the network, because the modules are doing their own firing, so you can get very fast, reliable timings for your shows. So non-autonomous systems, this is probably people know more about these type of systems than the autonomous ones. So this is where the firing controller or the PC sends all the firing commands out. So if you get the laptop and you pull the cable out, the show will stop. So yeah, the firing modules will respond to the network commands sent out. So as your show's going through and it's stepping out, it's saying, right, on the network, it's saying, right, fire this, fire that, and the modules are sitting there responding and to the messages for them, firing the particular cues that they need to fire. And again, you're limited to the speed of the network and the controller, so the modules can only fire as fast as the network and the controller can send the commands out. And again, it's very highly reliant on the network latency being constant, because if you've got you're sending a packet of data and you've got to say fire here, and then it's got to bounce around a whole load of places and come out, and it's offset, then that can cause problems. And also, non-autonomous systems, the protocols can be more complicated because you need to send commands to say, fire. Fire a queue on this module, but also fire a queue on this module, and this module, and this module. So if you're trying to make a whole front go at once, obviously the protocol has to be a bit more clever about how it deals with firing multiple things at the same time. Whereas on autonomous systems, they don't care what all the other modules are doing. They just do their own bits, and if you've programmed it to have a whole front go at once, the whole front will always go at the right time. I've added this in. So the system I built at uni was what I called a hybrid autonomous system, where what it actually did was it when you designed the show, it created basically a list of sequence numbers, and each of the modules then had their parts of the show uploaded to them, and then all the firing software did was, rather than saying fire this queue, fire that queue, it would just say fire sequence 1, fire sequence 2, fire sequence 3, and the boxes would just sit there and say, right, have I got anything for sequence 1? No, well, don't do anything. Have I got anything for sequence 2? Yep, well, I need to fire 2 queues, and it would load it in and fire them. And this meant that the protocol was very simple, because all I had to say was, right, fire this sequence, and the boxes knew what they were going to do. But it wasn't autonomous because the boxes couldn't do anything on their own. All they knew is that they had these set of sequences they had to fire, and when they received that fire signal for that sequence, they would just output the particular cues they need to fire, and that's what they needed to do. So that's how my first digital system worked, and I kind of call that hybrid autonomous. So there's a little bit of a comparison here. Autonomous systems, if you lose the network communications, you have problems shutting the module down, and this is where the health and safety part comes into it, because if you've got a system that's sitting there and it's programmed with a 10-minute pyromusical, and for some reason you lose communications to it, that box is going to sit there and fire 10 minutes of fireworks, whatever you do, unless you've gone down and go and switch it off. So, yeah, but equally, pre-programming the modules means that these modules, you can turn them on and they'll say, right, these are the fireworks you've got connected, but because it knows what part of the show it needs to fire, it will tell you, right, you're supposed to have something in queues 1 to 10 and you have or you haven't. Whereas with a non-autonomous system, you've got to wait till you turn the laptop or the controller on to actually see if everything's wired in the right place. And also, because the system's pre-programmed, you can actually trigger it without the controller. So this system here, you can actually put just a bit of wire and a battery, and each time you pulse it, it will fire the next sequence for you. Or if you're doing a pyromusical, you'd have one sequence and you could trigger it. But because the module knows that it's part of the show, it's a very nice redundancy feature. Whereas with a non-autonomous system, if you take the laptop and throw it away, the firing modules can't do anything because they don't know what to do. So a non-autonomous system where the data is being sent from the laptop, if you blow a cable, you'll lose that part of the show. Queue checking, like I said, can only be done with the controller or the laptop plugged in and all the modules connected together. And without the controller, the firing modules are useless. So solutions to some of these problems. So if you've got non-autonomous where the laptop's sending the commands out, you can segment the network. So you can have one cable that goes off this way, one cable goes off that way. If you read the articles about the fireworks in London, they segment their network on the eye. So I think there's either 3 or 4 separate lines, and every, say, third module picks up one cable. So they have 3 cables that go around, and that way, if they lost one of their cables, they would only lose a third of the eye. So there is a really good article, it was in Fireworks magazine or something a while ago, I think. But they explained a lot of the technical side behind this. So segmenting your network can help solve this problem of if you blow a cable apart, you don't lose all your show. Routing cables carefully is obviously a good way of solving that. So autonomous. So the biggest problem with these autonomous systems is if you have an issue and you can't shut the system down, you can't just run out into the field and go and switch all these modules off. So what we do is when we're running fully auto, we run the system wired, and the wired connector gives us a remote power up. So basically we run our network in a complete ring. So every single box is daisy chained together and it comes back to the firing point. The actual network communication is not connected, but the 24-volt power up is connected at both ends. So from our desk, we can flick one switch and every single module will turn on. And then if we need to power it down, we'll flick one switch and every single module will turn off. It's basically a relay across the main power switch.
Are you able to relay data as well?
It depends on the protocol, the network, but RS485 is specifically designed to be a bus. So you shouldn't really, you can get noise and other issues if you try and run it in a loop. RS485 is quite resilient, but the standards say you shouldn't run it in a loop. So the way we do it, we have 2 chances. If we can blow one cable and all the modules will stay on, if we blew another cable, then the modules between there would switch off. So that's how we get around this issue of having an autonomous box run away with itself. And you've got to consider, there's lots of sequencers and other things on the market that you can get. You've got to consider if you've got that sequencer sitting there firing a sequence of shells, how will you shut that off if you have an issue during the show? So I've talked about this is how we run our remote power up in a ring. With radio systems, of course, you haven't got a cable there plugged in to physically shut it down. So what some companies have done or are looking at doing is using a heartbeat. So that the laptop will send out a pulse on the radio every so often, and then the modules will carry on firing, and if they lose the heartbeat, then they automatically deactivate. And then if they start receiving the heartbeat signal again, then they'll reactivate again. So this is how with a radio system, you can implement some kind of auto shutdown if it stops receiving the signal from the laptop. So sort of health and safety things. You must have a complete shutdown for your system. There is no, if you end up in court because your shell rack blew apart for whatever reason and you're firing shells in the audience and you said, I couldn't turn the system off, I don't think that would wash. So I think that is a very important thing, and something that when we've been doing shows like this, we think is one of our top priorities. Is we need a way of completely shutting down the system if there's a problem. And also, you need to have a good understanding of when the system will actually Q check, because electric systems will fail, components will go wrong. You know, if you're using these systems use a type of component called a MOSFET, and quite often when they fail short circuit, which means they'll fail with current, so current will always pass through them. And the problem is that if your system switches on, so for example the Merlin one here, when you switch it on, it automatically Q checks at the beginning. If you don't realise that, and you're sitting there and you've got all your pyro around all wide in the box, and you flick the switch and you don't realise it's Q checking, there is potential at that point for it to fire the products. The same way with any system, that when it Q checks, it's putting current through. It's putting very low current through. But if there's a fault on the module, potentially at that point, you could have an issue. So certainly when we're Q checking any system, we always make sure there's nobody near any of the products while we're doing it, because that is a point where things can go wrong with any system. But you should really understand when is it going to Q check, when is it going to be doing it. I know some of the new systems, some of them don't tell you when it's doing it, and they're trying to be clever and doing Q checks so the data's all there when you need it. But in reality, you don't. My feeling is you don't want that to happen. So I think this is also important. I think when you're doing a fully, a pyromusical show and it's going really well, I always need to consider in my head what conditions will need to happen for me to be able to turn that switch, turn everything off and stop the music, because it's quite a big deal and there's a lot of pressure riding on people doing these shows, and it's too easy to potentially just sit there and let the show run on, and then if something happens and not actually switch it off. So I think it's important to consider before you're doing a show, before all the pressure's there, what are the conditions that I will shut this show down on. If you have a low break shell, is that a reason to shut down the show? Potentially it's not. If you have I don't know. I think all I'm saying is just think about it, because the pressure of the moment can sort of distort your decision-making abilities of when you've got to pull the plug, because nobody wants to do it, but at some point we all have to shut things down, and even that's from a health and safety point of view, from the wind or the whatever else. I'm sure Steve will tell you some stories about shows he's been sort of doing health and safety for, and he's had to tell them to shut things down, to stop the show and stuff. It's just something to consider, because the pressure can be there, and it does make it difficult, especially when you've been working for days and days and hours in the cold, and and also if you're running an autonomous, there's lots of sequences out there. Just think about how long are you happy for a sequence to run without a way of shutting this sequencer down. Is it 5 seconds? Are you happy to do a 5-second chase, or 10 seconds of shells? What is the limit to how long you want to run something that you have no way of shutting down? Because sequences can be really useful and they can do some really cool stuff. If you're just doing single shot mines and they're a good distance away, and the chances are that even if something went wrong, they wouldn't reach the crowd because of the types of products, maybe some flash pots or something like that, then that may not be so much of an issue as if you're running a whole set of shells and you've got a minute's worth of shells running off a sequencer. Obviously that would be a lot more of a big deal. And then sort of dead man's handle. So a lot of the systems that send all the firing commands from the laptop, their dead man is to literally just disconnect the network. So you can hold your dead man switch, and when you let go, it disconnects the network and the boxes don't get any firing commands. If you want to carry on again, you just hold the lever down again, the network reconnects, and then the modules start firing again. And like I say, for ours is a bit more of a kill everything. You flick that switch and everything dies. And again, it's a debate about whether a dead man is something you hold, like a proper dead man, so you hold it, and then if you have an issue, you just let go and it stops, or whether you're happy to have something where you have to actually go and physically switch something to switch it off. So there's two different types there. I think the real definition of a dead man's handle is something that if you die, it will switch off. And that's about all I've got to say about that kind of thing. Have you got any questions or thoughts, or did that make any sense? Is it useful? I've just blown your minds.
Thank you very much, Chris.
Cool.